morning everyone. Today we will learn about Dempster-Shafer theory. It offers a unique perspective on uncertainty, providing a mathematical framework for combining evidence and making decisions in situations where traditional probabilistic methods face challenges. In the earlier lecture we have discussed about the probabilistic methods. So, in this lecture we will be discussing the Dempster-Shafer theory. So, it was developed by Arthur Dempster in 1967 and later expanded by his student Glenn Shafer in 1976. So, it is a mathematical theory of evidence based on belief functions and plausible reasoning. So, it is used basically to combine separate pieces of information or evidence to calculate the probability of an event. Instead of traditional probabilities, it allows or it allocates a number between 0 and 1 to indicate a degree of belief on a proposal. This is known as belief mass. So, it provides an alternative way to traditional probabilistic theory for representing uncertainty. This distribution of masses is called belief basic assignment. In short, it is BBA. So, it represents a degree of belief represented as a belief mass and is distinct from Bayesian probability distribution, which we have studied in a previous lecture. It is designed to deal with distinction between uncertainty and ignorance. So, in DST, a degree of belief or also known as mass is represented as a belief function rather than a Bayesian probability distribution. It provides one of the numerical method to represent and reason about the uncertainty, and it offers a way to combine evidence from two or more sources and draw conclusions from them. So, in cases where there is a lack of sufficient data to accurately estimate prior and conditional probabilities as required by Bayes rule, it provides, that is Dempster-Shafer theory provides an alternative to us. So, instead of computing the probability of proposition DST, that is a short form of Dempster-Shafer theory, it computes the probability that evidence supports the proposition. It uses belief interval to estimate how close the evidence is to determine the truth of hypothesis. So, here the absence of evidence versus evidence of absence means DST incorporates the philosophy that absence of evidence is not the evidence of absence. It acknowledges that just because evidence for a proposition is absent, it does not necessarily mean that the proposition is false. So, we can say that Dempster-Shafer theory is a unique approach to handling uncertainty, especially in situations where traditional probabilistic method may fall short. It provides a systematic way to represent and reason about belief, combining evidence from different sources and addressing the nuanced distinction between the uncertainty and ignorance. The theory's flexibility makes it valuable tool in situations where detailed probabilistic information may not be readily available or estimable. We will see one example related to dealing with uncertainty using Dempster-Shafer theory. This is one of the terrorism investigation. So, imagine we are investigators trying to figure out which of the three terrorist groups A, B or C planted a bomb in a building. In a traditional probability framework, we might feel compelled to distribute probabilities in a way that makes them add up to 1, considering belief and disbelief as opposites. So, for instance, if we believe there is an 80% chance that group C is guilty. So, the probability for guilty of group C is suppose 0.8, then we might be forced to allocate the remaining 20% evenly to groups A and B, saying that each have a 10% of chance. This we used to do in the probabilistic theory. However, in a Dempster-Shafer theory, it offers a different approach. we are not constrained to distribute belief and disbelief in a strict complementary manner. This is a crucial departure from the traditional probabilistic theory. So, in our terrorism investigation example, we believe with a probability of 0.8 that group C is guilty, and instead of distributing the remaining probability equally to groups A and B, Dempster-Shafer theory allows us to leave this relative belief unspecified. So, it acknowledges basically that we may not have enough information or confidence to precisely quantify the probabilities for groups A and group B. So, in DST we can express our uncertainty by not assigning specific probabilities to these groups, that is group A and B. So, this is particularly valuable in real world scenarios where assigning precise probabilities might be challenging due to limited information or the complexity of the situation. So, DST allows us to express our belief without feeling compelled to distribute probabilities in a way that might not accurately reflect the true state of our knowledge. This is a key advantage when dealing with complex and uncertain scenarios such as in criminal investigation. We will see one scenario where evaluating hypothesis with evidence. Imagine you are in a scenario where you are trying to figure out the color of marbles in a bag. The possibilities are red, green and blue. Now, you gather some evidence and it strongly suggests that the marbles you picked are either red or green, and this evidence supports this is to a degree of 0.6. So, you have good reason to believe that marbles are most likely red or green, but here is a twist now. In a Dempster-Shafer theory, we do not necessarily need to allocate the remaining support to the specific color blue. We can leave some uncertainty there. So, if the evidence strongly supports red green to the degree of 0.6, it allows DST allows us to distribute the remaining support in a more flexible way. We can say that we believe in red, green, blue to some extent without committing fully to blue. It recognizes that we might not have enough evidence to be sure about the blue color. In contrast with the Bayesian model, in a traditional Bayesian model, if we do not allocate the remaining probabilities to blue, we typically assume that it goes to the negation or complement of the hypothesis in case of blue. So, this is more rigid approach as compared to DST, which is a flexible approach. It implies that if we are not confident about blue, we are more confident in its absence. So, we can sum up in this way. In simple terms, if you strongly believe in red green based on your evidence, DST allows you. So, summing up in simple terms, we can say that if we strongly believe in red green based on our evidence, DST allows us the flexibility to not fully commit to blue. So, we can express our uncertainty about blue. In contrast, a Bayesian model would typically assume that if you are not confident about blue, we are more confident in the absence of blue. This flexibility in DST is useful when dealing with scenarios where uncertainty is inherent and we might not want to make strong commitments without enough evidence. So, before moving to a few more examples and in details of Dempster-Shafer theory, we will understand the basic probability assignment in Dempster-Shafer theory. Suppose we have a group of 3 colors, blue, green and red. Each of these colors can represent a statement about something like the color of car passing by. So, in Dempster-Shafer theory, we want to assign probabilities to different statements about the color based on the evidence we have. Basic belief assignment, it is also known as basic belief assignment, and also we can call it as basic probability assignment, which is represented as M. So, this is like giving a score to each probability possibility ranging from 0 to 1 such that when you add up all the scores it is equal to 1. For example, suppose we are guessing the color of the car and have no strong evidence. So, we might assign equal scores to blue, red and green as 0.33, that is 1 by 3. So, what is the proposition in DST basically? A proposition is a statement about the color. There are many possible propositions like the car is blue or the car is not red and green. So, consider for 3 colors we have 2 to the power 3, that is, since there are 3 colors we have 2 to the power 3, that is 8 propositions including individual colors and its combination as well as the empty set. So, the various propositions are 1 blue, 1 red, 1 green, the combination of blue red, the combination of blue green, the combination of red green, the combination of red blue green and the empty set. So, these are the 8 propositions with 3 different colors. There is one term, that is belief in subsets. What it means that if we believe in particular color, we also believe in all the combinations containing that color. So, suppose if you believe the car is red, we might implicitly believe it could be red and green, it could be red and blue or even all the combination of 3 colors. The mass, that is M, represent, that is, it is considered as evidence support. It represents how much evidence supports a particular statement. Suppose that if you have strong evidence for the car being red, then we might allocate a higher mass to the proposition red compared to the blue and green, blue or green. So, we can say that this Dempster-Shafer theory help us to express our beliefs and uncertainties about different statements by assigning masses or scores to the various propositions. It is a powerful tool for dealing with uncertainty, making informed decisions based on the evidence. We will see here now the few basic terminologies that we will be using in Dempster-Shafer theory. One of the terms that we normally face is the frame of discernment, short form it is FD. What it means that the frame of discernment is like the world of possibilities or all the potential outcomes which we are considering. We can also consider this as a sample space. Suppose we are trying to guess the color of the car, the frame of discernment might be all possible colors, that is red, blue, green, etc. and so on. The term proposition also we will be using regularly. Propositions are the specific statements or subsets within the frame of discernment. For example, the car is red, the car is not blue and so on. So, this will be these are all propositions. Probability value and basic probability assignment. It is basic probability and assignment somewhere, it is BBA, basic belief assignments. So, these are the values that are assigned to each proposition to express our belief in each statement. For example, if we believe there is a 0.3 probability that car is red. So, we assign this probability as basic probability assignment M to the proposition red. Focal term is also one of the term that we will be using. Focal elements are the proposition with non-zero probability assignment. Non-zero means there should not be 0 assignments to the belief. So, these are the statements we believe in, that means these are the statements we believe in. So, if we believe in red with the probability of 0.3 and blue with the probability of 0.2, these are the 2 focal elements. There is also a term that is we call it as a core. It means that it is the union of all focal elements. It represents the set of propositions that we collectively believe in. So, if we believe in red and blue, the core includes both these propositions. So, suppose imagine you are trying to guess the color of a car at a distance. So, what is the frame of discernment is in this? All possible colors red, green, blue and many others. Proposition here it will be specific statements like the car is red or the car is blue, etc. And what will be the BPA or BBA? It is the assignment probability, assigning the probabilities like 0.3 to that the car is red. And what will be here focal elements? Statements we believe in, that is red with non-zero probability. And what will be the core here? The union of all focal elements representing our collective belief. So, we can say that it helps us systematically, that is Dempster-Shafer theory helps us systematically express what we believe about various statements or propositions within a given frame of sample space or discernment. It is like building a structured way to represent our belief and uncertainties, which is especially useful when dealing with complex scenarios. There are some properties of basic probability assignment. One of the properties this is phi represents the empty set. So, it is the basic probability assignment is equal to 0, which is can be explained as this is the BPA of empty set is always 0. This means we do not assign any probability to the scenario where nothing happens. So, for example, in a coin toss scenario where theta is the set of all possible outcomes, that is head and tail, the basic probability assignment to the empty set is 0 represents the case where neither head nor tail occurs. Another property of BPA is that is the summation of all basic probability assignment across all possible propositions such as subsets A of the frame of discernment theta is always 1. This ensures that we account for all possible possibilities. Suppose for the same example about the coin toss, if A is a set consists of head, tail and combination of head and tail, and the last one is phi, there are 2 to the power 2 propositions, that is 4 propositions, then the addition of all the basic probability assignment will be equal to 1. This covers all possible scenarios. We will further see this coin fairness assessment example. Suppose we are unsure that if a coin is fair or biased, the possible outcomes are head and tail. Here the frame of discernment, as we have discussed, is which is represented as theta, head and tail. The propositions A is all possible combination 2 to the power 2 propositions are there, which we have already discussed now. Then the basic probability assignment, that is represented as M, is we assign 0 probability to it being a head. So, M of H is 0, M of tail is 0, 0 probability for tail, and M of H and T, that it is equal to 1. It means that we are certain that it is either head or tail. So, the probability is 1, and the empty set, that is phi is equal to 0, that means no probability for none of these scenarios happening. Actually, what we are saying here, that we are saying that you do not think it is definitely head and therefore, it is 0, or definitely tail and therefore, we have assigned BPA as a 0, and we are pretty sure that it is either head or tail. Therefore, we have assigned the BPA, that is basic probability assignment, as 1, but we do not know which one, and here we are ruling out the possibility that neither head nor tail occurs, which is equal to 0, that is for the empty set. So, the basic probability assignment allows us to express our belief or uncertainty about various scenarios within a given frame of discernment. The properties ensure that we are covering all possibilities and not assigning probabilities where they should not be. So, the belief function, this is also known as basic probability assignment, is a belief function, which is a way to express how confident we are about the occurrence of proposition. So, for example, if we are trying to guess the color of a car, so belief in red might express how confident we are that car is red. belief in A represent the total belief committed to the proposition. Example, suppose if A is a proposition that the car is red, then belief in red tells us how confident we are in this statement. Another property of a belief function is that is belief in A union B should be greater than belief in A plus belief in B minus the intersection of A and B. This property ensures that the belief in the union of two propositions is at least as much as the sum of their individual beliefs minus their intersection. For example, if A is the car is red and B is the car is blue, this property ensures that our belief in the car is red or blue is at least as much as the sum of our belief in the car is red and the car is blue minus any overlap. So, we can say belief or possibility is considered similar to the probability that a proposition is supported by the evidence. Again we will see example of a car. If we have evidence supporting the proposition the car is red, that is belief in red expresses how much we believe in this based on the evidence. It is calculated as the sum of basic probability assignment, that is M, for all subsets of A. For example, if A is the car is red or blue, then belief in red or blue is calculated as the sum of basic probability assignment for red, the basic probability assignment for blue and the basic probability assignment for red and blue. So, we are trying to guess the color of a car, that is belief in red or blue, which is equal to basic probability assignment for red with the addition of basic probability assignment for blue and with the addition of basic probability assignment for red and blue. This expression captures how much we believe in the possibility of the car being red, blue or both. So, in summary we can say that the belief function, which is represented in short form as BEL, is a tool to express confidence in propositions based on evidence. Its property ensures consistency and reflect our certainty or uncertainty about the different situations. There is another term that we will be using regularly, that is plausibility. What it means that it is the probability that a proposition B is compatible with the available evidence. It represents the upper limit belief limit on the proposition. For example, if we have evidence that supports the car is, that is the color red and blue, the plausibility of the proposition is the car is red or blue would be high. So, that is the upper limit. With the help of the possibility, we will be representing the upper limit that the car is upper limit for the car is red or blue. So, this is it is represented as PL and in a parenthesis A. It expresses the upper belief limit on proposition A. It represents, another way it represents the extent to which the proposition is credible or plausible. If, for example, suppose if A is the car is red or blue, which is represented as PL, that is in a bracket red comma blue, would indicate how much we find this credible, this proposition credible based on the evidence. So, there is a function to express the credibility, which is calculated by summing the basic probability assignments. There is a function to express the credibility, which is calculated by summing the basic probability assignment M for all subset of B where there is non-empty intersection with A. It represents the support that can move into A. For example, if A is the car is red or blue, then the plausibility of red blue is calculated as the sum of basic probability assignment for red, the basic probability assignment for blue and the basic probability assignment for red and blue and any other subsets that intersects with red blue. For the calculation of plausibility, we will see one example here. we are trying to guess the color of the car. So, calculating the plausibility will be for the red and blue, plausibility for red and blue will be equal to, as we have discussed now, that is the plausibility for basic probability assignment for red with addition with basic probability assignment for blue, added with basic probability assignment for red blue, added with basic probability assignment for red green, and where all and plus the basic probability assignment for red blue and green. It means that wherever in a subset the red and blue occurs, all the basic probability assignments will be added to it. This expression captures how plausible or credible it is that car is red or blue based on the evidence. There is a relationship between the belief function and the plausibility function. The plausibility is always greater than or equal to belief. Why so? Because we always, plausibility is the upper limit of your belief, means up to what extent you are believing on some propositions. So, the plausibility considers all possible subsets that supports the proposition, making it equal to belief when there is no subset that supports the negation of A. So, here we can say that plausibility of red blue will be always greater than the belief of red and blue. There is a term, that is credibility status representation, which is represented as the interval between the belief and the plausibility. It represents the credibility status of A. It shows that the lower limit and upper limit, first term is lower limit and the second term is the upper limit. So, example would represent the range of belief and plausibility for the proposition that car is red or blue. So, the first term is belief on car is red or blue, and up to upper limit will be believing whether the car is blue or red will represent the plausibility. Plausibility minus belief represents the uncertainty in the occurrence of A. It captures the range between the belief and plausibility. So, that is if we subtract the plausibility and belief, then it will represent the uncertainty in occurrence of any proposition. For example, if the plausibility of red blue minus the belief of red blue is equal to 2, 0.2, it indicates some uncertainty in our belief about the color of the car, that is 0.2 is indicating some uncertainty. So, summing up, plausibility is a measure of how compatible a proposition is with available evidence. It provides an upper belief limit, and the relationship between the belief and possibility reflects the uncertainty in our understanding of proposition. We will see the concept of belief interval and how it represents confidence in a proposition. So, the belief interval represents a range of confidence or belief in a proposition. It consists of two values, belief and plausibility, which denotes the lower limit and the upper limit. If a car is red, for example, or a blue, the belief interval is belief for red blue, and the plausibility of red and blue would show that the range of how confident we are in this proposition based on the evidence. We will see now the different situations where we will understand the belief interval. We will try to understand various belief interval in various cases. Suppose the belief interval is 0, 1, that represent the total ignorance. If the belief interval is 0, 1, it means we have no belief in support of the proposition to total ignorance. This interval suggests a wide range of uncertainty, indicating that we do not have enough evidence to form a strong belief. If the belief interval is 0, 0, it means we believe the proposition is false. This suggests strong evidence against the proposition. If the belief interval is 1, 1, it means we believe the proposition is true. This suggests strong evidence in the favor of proposition. If the belief interval is 0.3 to 1, it means we have a partial belief that the proposition is true. The lower limit 0.3 suggests some uncertainty, but we are confident to some extent. The belief interval 0 to 0.8 means we have partial disbelief in the proposition. We are not entirely convinced it is false, but there is some doubt. And the belief interval 0.2 to 0.7 means our belief is influenced by evidence both for and against the proposition. There is a balance of evidence leading to a range of uncertainty. The width of belief interval is good aid in deciding when more evidence is needed. A wider interval indicates greater uncertainty, suggesting a need for more information. So, it provides a range of confidence level in a proposition reflecting the uncertainty based on available evidence. Understanding the interval width helps in gauging the strength of our belief and deciding whether additional evidence is required or not. Now, we will see the Dempster rule of combination. So, this allows us to combine basic probability assignment values from two independent sources or bodies of evidence and draw conclusions. For example, there are two different sources which is represented as 1 and 2, two belief functions provided by two independent sources B 1 and B 2 over the same frame of discernment. So, let belief 1 and belief 2 be the two belief functions provided by two independent sources of evidence B 1 and B 2 over the same frame of discernment, and their corresponding belief probability assignment M 1 and M 2, then the combined global belief function denoted as Bell is equal to belief 1. This XOR is not actually XOR, that is a multiplication we will be seeing with the example, combined with belief 2 is obtained by combining the belief basic probability assignment for M 1 and M 2 through the following Dempster rule of combination. This is what the rule of combination, that the combined rule of combination will be from mass from the source 1, basic probability assignment from the source 1 and the basic probability assignment for source 2 for that particular proposition, where the numerator and denominator can be said as the numerator captures the intersection of A and B that results in C. The denominator normalizes this by considering the amount of non-zero mass left after the intersection. The combined global belief function takes into account the basic probabilities values M 1 and M 2 from both sources and provides a unified belief function that reflects the combination of evidence. Dempster rule of combination is shown as in the formula. We will see one example scenario where two independent sources provide evidence about the color of a car. So, belief in red is equal to the summation of M 1 for A and M 2 for B, where A and intersection B is equal to red normalized by the amount of non-zero mass left after the intersection. Similarly, belief in 2, that is the color, represents similar calculations for the second source also. The combined belief for that color red is calculated using the Dempster Shafer rule of combination. So, let us understand the result. The result for that color represents the combined belief function that considers evidence from both sources. It helps in drawing the conclusions about the color of the car. So, it is a way this Dempster rule of combination is a way to combine evidence from independent sources and create unified belief function. The numerator captures the intersection of evidence and the denominator normalizes the results. So, we can say that the rule of combination combines the basic probability assignments M from two pieces of evidence to create a new belief function that represents the combined evidence. For example, let us say we have two pieces of evidence M 1 and M 2 regarding the outcome of coin toss. So, M 1 is an evidence with head as 0.5, which evidence 1 supports the idea that the coin is head with the probability of 0.5. Evidence 1 supports the idea that the coin is tail with a probability of 0.5. Second source of evidence, which is represented as 2, is evidence 2 supports the idea that the coin is head with the probability of 0.3, and evidence 2 does not support the idea that the coin is tail. As you can see in the table, there are 2 sources of evidence for a coin toss, 2 different sources, one is 1 and other one is 2. It is represented in the table in the form of rows and columns. The column, the first column represents the first evidence, and this first row represents the headings for the second evidence. So, as you can see, so I have represented this in the form of a table, the 2 different sources and its basic probability assignment. So, the heading of row represents M1, the headings of first column represents M2, and the cells of this table represents the combination of 2 different sources. Like for example, the cell number 1, where it is represented as head, which is equal to 0.15. It means that we have combined the 2 from 2 different sources, M1 and M2 for head is 0.5 and 0.3, that is the product of 0.5 and 0.3, that is equal to 0.15. Similarly, we have calculated for all the cells, and also we will say here that it is an intersection of 2 different sources. Like for example, in the second center cell, where in the second column where it is equal to empty set, which is 0.15, it means that the intersection of the second column and the third row, that is tail, there it does not have any common proposition. Where in the it is in the first column it is tail, in the row it is head. So, and there it does not have any common proposition. So, it comes out to be empty set. Similarly, like for example, the last bottom right cell, okay, where it is head and tail is equal to 0. Why it is 0? Because the product, if you see, the last row has a proposition head and tail, and the last column has the proposition head and tail. For the first evidence, the proposition basic belief is 0.7, and for the second evidence, the head and tail proposition is 0, and so the product of these 2 is 0. And since the set has 2 same common proposition H and T, and therefore, it does not have an empty set, it is H and T. So, here it will, where we will always see the intersection for the different sets, and the cell will have that intersected set propositions. So, the rule of combination calculation for head is M1 of head comma M2 of head will be equal to, that it is 0.15 plus 0.35 divided by 1 minus 0.15 plus 0. This 1 minus 0.15 plus 0 is for the empty set. All the empty sets in a table will be added. This calculates the combined belief for the proposition the coin is heads based on both pieces of evidence. The combined evidence suggests that coin being head has a belief of 0.58. Similarly, for the calculation of tail, we will see from the table where all the sets have tail, and summing up all the sets has tail, it comes out to be 0.5 divided by 1 minus, where 0.15 plus 0 is all the cells where it has an empty set. This calculates the combined belief for the proposition the coin is tail based on both pieces of evidences. So, the interpretation can be, the combined evidence suggests that the coin being tails has a belief of 0.42. The rule of combination takes into account support for head and tail from both pieces of evidence and provides a new belief function that reflects the combined strength of belief. Now, we will see, let us understand the denominator, what is that 1 minus that empty sets all the additions of summation of empty set. This is a degree of conflict which I have represented as K12 between the two sources of evidence B1 and B2 and its significance. The degree of conflict is denoted as K12 and it measures the level of disagreement or inconsistency between two sources of evidence. Meaning that the value of this degree of belief is determined by summing the product of basic probability assignment values M1 and M2 for each possible intersection of sets A and B. The higher the value of K1 to the higher the value of degree of belief, the greater the conflict or inconsistency between the two sources, and so we are trying to actually normalizing by subtracting 1 minus all that empty sets in a table. The normalizing factor adjusts this combined belief function to eliminate the conflicting pieces of information consistently with the intersection operator. So, what it means that when it is high, that is degree of conflict is high, close to 1, the normalizing factor reduces the impact of conflicting information, making the combination more consistent. So, what is actually the significance of this normalizing factor? It eliminates the conflict. What? The normalizing factor acts to eliminate the conflicting pieces of information between two different sources that has been combined. This adjustment ensures that the combination of evidence is consistent with intersection operator. And when this K12 is equal to 1, it indicates that the combined basic probability assignment does not exist. Bodies of evidence B1 and B2 are said to be in full contradiction. This situation arises when there exists a subset A is a proper subset of theta, that is frame of discernment, such that a belief in 2 is not for not A is equal to 1. We will see one example of flu, cold, pneumonia and allergy, which is given here as initially with no information our belief function m is theta 1.0, then second belief m1. After observing fever, our belief function m1 becomes flu, cold, pneumonia with 0.6 and therefore, the frame of discernment, that is theta is 0.4. Belief after observing a runny nose m2 is allergy, flu and cold is 0.8 and theta is 0.2. Combine m1 and m2 to get m3. Using the combination rule, we get a new belief function m3. So, you can see in the table we get an m3 after using the rule of combination. We get flu cold 0.48, allergy, flu cold 0.32, flu cold pneumonia 0.12 and theta is 0.08. So, belief after observing the problem goes away on trips is m4. After observing that the problem goes away on trips, the belief function m4 is allergy has given the belief value 0.9 and let theta is equal to 0.1, which is the addition of both is equal to 1. So, combining m3 and m4, as you can see in the table, we get m5. Using the combination rule, numerator and normalizing, we get a new belief function m5. So, what is an m5? As you can see in the table, flu cold is 0.104, allergy flu cold is 0.0696, flu cold pneumonia that is 0.026, allergy is 0.782 and theta is 0.017. So, what is actually what we will interpret from all these values? The belief plausibility of allergy is calculated based on the combined evidence from observing fever, runny nose and the effect of the problem goes away on trips. The process involves combining belief, normalizing and calculating the belief possibility for a specific condition based on the available evidence. So, it provides Dempster-Shafer theory provides basically a formalism to express both uncertainty and ignorance. It allows for the representation of partial belief and lack of information regarding the certain propositions. It is a combination tool that allows the combination of evidence from different sources. It enables the integration of information even when sources may have conflicting or incomplete information. It can address questions related to necessity and possibility, providing a more nuanced perspective compared to the Bayesian approach. This is particularly valuable in situations where reasoning about uncertainty and possibility is crucial, but unlike Bayesian methods, DST does not require prior probabilities. This can be advantageous in scenarios where obtaining reliable priors is challenging or impossible. It is well suited for reasoning in rule based system. It can handle situations where rules may be uncertain and conflicting, making it applicable in domains where expert knowledge is integrated into a rule based framework. So, we can say that DST offers a way to handle situations where prior probabilities are unknown. While a uniform distribution cannot be used in absence of priors, DST provides a means to work with uncertainty even when the full probability distribution is not available. So, it excels in scenarios where information comes from diverse sources with varying levels of reliability. It provides a framework to integrate evidence from different perspectives or sources even if they have different degrees of credibility. It is a rule that can handle conflicting information by assigning degrees of belief to various propositions. This is crucial in situations where sources may provide contradictory evidence. It has found application in various real world scenarios including healthcare, finance and natural language processing. Its ability to handle uncertainty and combine evidence makes it suitable for decision making in complex situations and uncertain environments. Hence, a Dempster-Shafer theory offers several advantages including its ability to represent uncertain and ignorance combined hence, a Dempster-Shafer theory offers several advantages including its ability to represent uncertain and ignorance, combine evidence from different sources, addresses questions of necessity and possibility and handle scenarios where prior probabilities are unknown or hard to obtain. Its application in rule based and real world environment further underscores its practical utility. As all has advantages, it has disadvantages too. Some limitations of Dempster-Shafer theory. The computational complexity of applying Dempster's rule can be high, especially when dealing with a large number of proposition of evidence sources. This can impact the efficiency of reasoning and decision making process. DST assumes that the sources of evidence are independent. However, in real world scenarios, sources may be dependent, leading to potential issues. Dependence can result in misleading or counterintuitive results, especially if correlation between the sources is not well understood. The normalization step in Dempster-Shafer theory has been criticized for losing some meta information. This step may oversimplify the handling of conflicting evidence and can be controversial in certain applications where preserving such information is crucial. It can be challenging to develop a precise theory of utility within the framework of Dempster-Shafer theory. The concept of belief in DST is not precisely defined with respect to decision making, making it difficult to integrate DST seamlessly into a utility based decision theory. And the Bayesian approach, which is widely used and well established, can perform tasks similar to confidence intervals. So, Bayesian methods allow for examining how one's belief would change with the acquisition of more evidence, and DST in this regard may be perceived or as less explicit in handling uncertainty associated with changing belief. So, it introduces implicit uncertainty associated with various possible changes which might be challenging to quantify precisely. The handling of uncertainty in DST, while providing a flexible framework, may lack the clarity and precision offered by other approaches. It can be sensitive to the choice of initial belief. The lack of well defined method for determining initial belief can lead to variations in outcome based on the starting point. So, everything depends on the starting point of belief, introducing a degree of subjectivity. DST has limitations in formally representing and handling dependence between a piece of evidences. The lack of robust formalism for dependent evidence. So, in summary, while Dempster Shafer theory offers several advantages, it also comes with computational challenges, issues related to the dependence of evidence sources, controversies in the normalization step, difficulties in developing a theory of utility, and comparisons with more established Bayesian approaches. The cons highlights areas where improvements or alternative methods may be considered depending on the specific requirement of the given application. So, that is all for Dempster Shafer theory. Thank you.